So having understood in the first video of the series what the problem is associated with analyzing building energy use, let's now use the UT's own analysis module to do this more elegantly. So here's a new measurement and verification analysis module. We'll open that up. And the first thing we have to assign is a baseline model. So we're going to do the same thing that we did earlier, namely look at the original power consumption, then we'll look at the power consumption after the retrofit, and then the UT will automatically compare the two for us. The first thing we're going to select is the base channel folders. Again, we have no particular folder structure in this model. There's not much data in here other than the 3 channels that were imported from the sample data. And we have to assign an independent variable and a dependent variable. Like we said, in many buildings, the energy consumption is weather dependent. So the dependent variable is the power, building power consumption. So it's our base kW data. And the independent variable is the weather, because the weather does not depend on the building. So it's completely independent of what the building does. This data runs roughly from March 1st of 2008. So we have the option of taking a smaller window of the data if some of it turns out not to be usable or runs into the construction period, through June 22nd of 2008, but in this example we're going to use all of it. And then we can correlate the outside air to the building energy consumption with the model builder. And we saw earlier on that we already made a filter for occupied and unoccupied data. So we'll start with the occupied data and let the UT compute what the correlation between the two is. So it does that internally. We'll look again in a second at how this works in the segment count, but let's look at the results first. It's a little bit hard to read again on the small screen that I'm using for the demonstration. So I'll get rid of this legend and zoom in a little bit. But what this shows is a correlation between outside air weather, which is shown here in blue, the building energy consumption in red, and then the predicted energy consumption that the Universal Translator has modeled now, and saying if I didn't have building energy consumption data, I could predict what it would be in this green line, which of course becomes relevant for the post retrofit data when I'm going to use this green data to compare against the new measured data. So I first have to create a baseline model that I can use for the second half of my analysis. So this looks like a very good fit already, R of 0.7. The only issue I see, for example, is right here. There is almost no energy use, or very little energy use compared to normal operations. And so the model predicts a much higher energy use based on the outside air. This looks like a holiday, actually. So I'm going to find a couple more of these, I think. Here's one. This is on March 28, and I can look. There's another one here on May 26. So March 28 and May 26 are holidays. So what I'm going to do is add those days to my filter. So I'm going to open it back up, add a bin. I'm going to call it holidays, and add an absolute date for March 28 and one for June 26. Having done that, I'm going to close the filter again and maybe close and reopen the MNV analysis module as well, just to make sure that that gets transferred correctly. Okay, and then I'm going to look at my occupied bin again, recompute, and take out the legend. And the date for March 28 is now still in here. I can see that over here. The prediction is still part of my model. What's happened is, and this is a little unique unfortunately to the way the UT does its filter bins, is that the order in which they're defined matters. So the occupied filter is still the first that gets looked at, followed by the holidays, and then everything else that's left is in the default. We want the holidays taken out first. So in order to do that, I'm going to have to go back to my filters and make sure that the holidays are defined before the occupied data. So I'm going to delete this bin and redo it, unfortunately, 8 a.m. to 6 p.m. So I'm going to re-add this bin, call it occupancy. And add my 8 a.m. to 6 p.m. on Monday, Tuesday through Friday. Okay, and then I'm going to open up my MNV module again, take another look at just the normal occupied data, take out the legend once again, and now it's done correctly. So this week is now short. That March 28 date has disappeared. A little unintuitive, unfortunately, but that's the way the UT works. Whatever gets defined later also gets treated later in the order in which the filter is processed. Okay, so what I can look at in addition to the time series graph here, which shows me how the UT calculates its prediction of energy data based on weather, is a couple of different presentations of the same data. So here is the model data and the predicted data versus the independent data. And this is basically a scatter chart of the original data in red. So here's the outside air temperature. And the original data is now modeled in 6 linear segments. So this is how the UT determines its calculation method for approximating this red scatter chart. If I took a different number of segments, let's say 2, and I recalculated that, I would see 2 linear segments. And the less segments I take, the less accurate this is going to become. So I'm going to go back to the default of 6. But the idea of presenting this data at all, it's kind of under the hood, is the slope at the end of this approximation, because this tells us in the manner in which the UT approximates its model. But we're going to come back to this later. So this is somewhat of a technical chart. A more simple model would be to look at the dependent versus the predicted data, which means the dependent variable is the power data for the building, and the predicted is the data that the UT calculates based on the weather and the time of day to get as close as possible to that power data. So a single line here at 45 degrees would be a perfect model. And I'm looking for a cloud that's as narrow as possible for a good model. So this is a very good model here, which we can also see again in the R-squared value of 0.88, the 4% error. Another chart I can look at is the dependent and predicted versus the independent model. So this is basically a scatter chart just overlaid. Here's the outside air temperature and KW data for both the original model, which is blue, and what the UT calculates based on the same weather and time data in red. So again, you see it's a very good fit. So there is the model that we have created for the baseline. We can therefore pretend that we understand how the building works at any given time of year and any given weather data, even if we don't have measured data anymore. But that's only for the occupied period. So we have to do the same thing again for the default, which is at night. I'm going to go over here, model the default period. I'll take out the legend again. Here's my nighttime data. Zoom in here real quickly so I can see the gaps here where the daytime occurs. And I'm going to take a quick look at how well that model works. So here it's a little less good than the original fit, I think, but here's again a sort of 45-degree line and the overlay of both. So it's a pretty good fit. Lastly, I'll do the same thing for holidays. And there are those 2 single days. So now, having completed a model for each of the various time periods that behave differently for the building, I'm going to take all the bins and combine them into a single model. So I click all the bins, go to the model assembler, and say combine. And that gives us the overall model. So for both occupied, unoccupied periods and holidays, we now have the behavior of the building well understood, as it were. Do a final check how well the model fits. So that's almost exactly a 45-degree line. So that's a very good fit. And that means we now have a model for the building for any time of day and any kind of weather. And that's what we're going to do when we compare the building against the post-retrofit data, because we will do that at a time when we don't have original building data measurable anymore because the retrofit has taken place. But now with this model, we can just calculate what the original building would have done under the same conditions. So there's the base model. We're going to now do the same exact thing for post-implementation. So we're again going to choose the independent variable. That is now the post outside air temperature, and the dependent variable is the post KW data. This is a slightly shorter period, runs from October 23 through November 28. And I will use the same filter, except I will ignore the holidays. Model the occupancy first. Quick double check of the data. I don't see any particular odd periods in this set. So I don't need to model holidays. I'm just going to go model the default as well. And then with default and occupancy bin selected, but not the holidays, I can ignore those. I'll go to the model assembler and combine them for the post implementation model as well. Okay, once again, I can see a very good fit between the modeled data and the actual measured data. Which I can also see in the scatter chart, very good overlay, or maybe the scatter chart of both of those, the modeled and the predicted against each other, which is again 45-degree line. So both the pre and the post model are very good. And with those, I can now look at the avoided energy use. So that is a grand total of something like 32,000 kW hours, 32,000 kilowatt hours, over the period of measured post data, which is something like 6 weeks, roughly 5.5 weeks. Of course, I'd be interested in knowing what it would be on an annual basis. And that's also the reason we went through the trouble of modeling the post-implementation data. I mean, we have that measured, so we could simply have compared the baseline model against measured data. But to extrapolate over a whole year's worth, we want both of those modeled, the behavior of the building before and the behavior of the building after the retrofit. Because with that, we can now take a new independent variable, which is the weather, in this case TMY data, so standardized weather data for a whole year, and compute what the savings would have been for a whole year. So we can pretend that we know how the building would have behaved in its original state for a whole year, even though we didn't have that measured. And we can also pretend that we know how the building would behave for a whole year after the retrofit, even though we didn't have that measured. Those two items are actually usually very complicated to do, and the UT does them as part and parcel of this analysis. So that yields a grand total of about 780,000 kilowatt hours. There is something we do need to look at for the way that this is modeled, to do some error checking, and the slope of these curves tells us a little bit about the accuracy of the model. And it shows us that down here, where we, for instance, look at negative savings, that tells us that the model is incorrect here. We obviously wouldn't run with negative savings in the building. It isn't going to produce energy. So in the next video, we'll look at how to trim the model a little bit to get rid of these errors.